Okay, in this lecture video, we are going to be talking about termination schemes or some tricks that we might employ on a transmission line in order to reduce some of the damaging impacts of a mismatch between the transmission line and the load, or between the transmission line and the source. So I've split this lecture up into three pieces. In the first, we're going to talk about ringing, the causes for ringing. We talked very qualitatively about it before, but we're going to sort of dive a little more deeper into that. In part two, we'll talk about two different tricks that we could use to reduce ringing or to improve the match from a generator to a load, and those are called series and parallel matching. And in the third part, we'll talk about two more tricks with more complicated schemes called capacitive and diode matching. So let's start with part one on ringing. So I showed this a couple of times before. And ringing is basically what you are seeing here in these figures. So if you've ever used an oscilloscope and you've sort of touched the lead or the probe to some place on a circuit that you know had a digital pulse or a square wave or something like that, but what you saw on the oscilloscope was maybe not a perfect square wave, but it looked a little messier like this. In this plot on the right, where we should see a brick wall going from +1 to -1. Instead, we see sort of a transition, and it overshoots and oscillates back and forth and slowly steadies out. Eventually, when the flip comes back to the positive side, it reverses, but again, you get this overshoot and oscillation back and forth before it settles out. So this is a known phenomenon. It's called ringing. And perhaps when you saw it at the time, you kind of waved your hand and said, whatever, bad oscilloscope, weird components, and you sort of waved it off. And of course, if you're looking at this in a lab class on a bench, on a comfortable, Friday afternoon, it might not mean so much. But if this exists on an integrated circuit or on a circuit board, it could be very problematic if you think about it, right? And there's a number of detrimental effects. The first is that we can get false flips from 1 to 0. Right? Imagine, take this plot on the right and make the ringing just a little bit more severe. And now we're at the point where if our digital logic circuit is set to trip at 0 to decide whether it's a 1 or a -1, then we might get false flips, right? That ringing is basically going to look like a 1 to 0, 1 to 0 flipping back and forth, when that may not be the actual, correct reading. This also is going to limit the speed of everything, since in principle, we've got to wait for this ringing to settle out enough before we can move on to the next clock cycle, the next bit flip. And if the ringing is too severe, we may have to wait too long, and that's going to slow us down and slow down our speed. And finally, electronics are typically only managed to or designed to withstand a certain voltage range, right? If you take a transistor and you power it up to 5 volts, there's some voltage you could place on that transistor that is going to break it down and destroy it, right? I don't know, it could be 6 volts, it could be 8 volts, it could be 50 volts, right? It's different for different components. And this ringing is basically giving us voltages that are beyond the power supply. And that has the potential to damage digital electronics and electronics in general. All right, so let's talk about the sources of what causes ringing before we get into where we're gonna get rid of it. So let's draw out another circuit right here. That's sort of our baseline of a voltage source with voltage value VG connected to an internal resistance of the generator, denoted with RG. And now we've got transmission line here. This is connected to. And this voltage source I write and often describe it as a battery, but it's not just a battery in the strict sense of the word. It also could be the output of a transistor, which is itself basically acting like a DC source. And so it could be the output of a logic gate. It could be output of an analog circuit. It could be output of a NAND gate or anything like that, that leads to a trace on the circuit board that terminates in what we're going to write down as a resistor on the load. But again, that resistor could not just be a resistor. It could be the input resistance to a transistor, or the input resistance to a NAND gate, or to an op amp, or to lots of things. But it has a certain finite value to it. Now, typically, if you think about this from a pure design perspective, if Z0 is our transmission line impedance, then it would be helpful for the generator resistance to be a small number, right? That's probably a good thing because we don't want to waste voltage, we don't want to waste current running across this generator resistance. And so it's advantageous to keep this value as small as we can. The load resistance, on the other hand, it's generally advantageous to make that as big as we can because we want to be sure that if VG is 5 volts, we want that 5 volts to appear almost entirely on the load. And if RL is pretty small, then we're going to have a resistor divider between RG and RL eventually, and we're not going to get much voltage on RL, and that's going to be problematic. So it's advantageous to have a small value of RG and a big value of RL. Now Z0, the transmission line impedance, let's say it's probably best to have this medium, right? It's going to be somewhere in between. 50 ohms, 75 ohms, 25 ohms, very common values, maybe 100 ohms, very common values for transmission line impedances, right? Whereas generator resistances, we probably want to keep that in single-digit ohms, if not less. And load resistances, we like that to be thousands of ohms. And so Z0 is probably going to be in the middle. So let's think about what happens in terms of reflection coefficients, right? So we got a reflection coefficient here of gamma L, the value at the load, which because the load resistance is bigger than a transmission line impedance, is going to be definitely a positive number, but it's probably going to be something close to +1, right? Maybe 0.9, maybe 0.8, but it's going to be pretty close to +1. On the flip side, there is also a reflection coefficient at the generator side, which we're going to call gamma G. This is going to be not a positive number, but a negative number because the generator resistance is smaller than the transmission line impedance. So this is a negative number, probably approaching -1, maybe -0.9, maybe -0.8. Okay, so this is the structure that we expect if we just sort of pursue the basics of how we deliver power and voltage to that load most effectively. So with this in mind, let's kind of draw out what a bounce diagram might look like for this case, right? So I'm going to start out with 2 vertical lines. And let's say that, just to put some numbers to this, let's say that our load resistance gives us a gamma L of, let me just give it an actual number, of 0.9. And let's say we've got a really good generator voltage that's awfully small, and let's take gamma G to be equal to -1, right? That will be the case if RG is 0. We expect this value to be -1. So let's take this as a numerical example. Let me get rid of this here. Let's take this as a numerical example and then examine what's going to happen in this case. All right, it's here. Gamma L is 0.9. All right. Now let's also say that the voltage we're working with is 1 volt. And by the way, this gamma L equals 0.9, this could come about from, as an example, Z0 equals 50 ohms and RL equals 950 ohms, right? That would give us a reflection coefficient of 0.9 at the load. So let's track what's going to happen in this case, right? So we're going to start out, we're going to inject the voltage into this circuit. That voltage is going to be, take this 1 volt from the generator and apply a resistor divider between RG, which is 0 ohms, and our transmission line impedance, which is 50 ohms. Well, that's an easy resistor divider rule to do. All the voltage is going to appear across the transmission line. So this is going to be 1 volt moving that way and encountering the load. When it reaches the load, we're going to get a reflection. It's going to work backwards. The reflection is going to be moving in the negative direction. And we're going to take that 1 volt and we're going to multiply it by 0.9. So this will be 0.9 volts right here. And let's just repeat this process. We're going to have another reflection that goes back. And this value is propagating again in the positive direction. We'll take this 0.9 volts and we'll multiply it by the generator reflection coefficient. So this becomes minus 0.9. All right, and let's just do this one more time. This will reflect here and become a negative 0.81 volts. All right, so let's track what's happening to the voltage on the load. All right, it's going to start out for the first period of time, it's going to be 0 volts because the first wave that's coming from the generator has not yet struck the load side. When it hits the load side, we're going to take this 0 volts, we're going to add the 1 volt that comes in, and we're going to add the 0.9 volts that's reflected. So after this point right here, we're going to have a load voltage of 1.9 volts. Again, take 0, add 1, add 0.9. All right, then this wave reflects back and forth, and lo and behold, a negative 0.9 volt wave comes in and reflects to form a negative 0.81 volt wave going out the other way. So we're going to take 1.9, we're going to subtract 0.9, and we're going to subtract 0.81. And that works out to 0.19 volts. The next one, by the way, I'll save you the trouble of calculating itself, works out to be 1.729 volts. So let's plot what the voltage on the load is as a function of time. This is time right here. And this is VL. And let's plot this in red. All right, it starts out as 0, and then it flips up. Whoops. Starts out at 0, and then all of a sudden it flips up to be 1.9 volts. And then we're going to wait. This will be 1 delay time. We're going to wait till 3 delay times. And then it's going to come all the way down to 0.19 volts. And then after 5 delay times, clean that up a bit, 0.19 volts. At 5 delay times, it's going to jump back up to 1.729 volts. And you can see what's happening here, that this process is going to repeat over and over again. So this is ringing, right? This is an overshoot and an undershoot and overshoot and back and forth. You can see that it is converging, right? It first overshoot was at 1.9. The next overshoot was at 1.729. The next overshoot is going to be a little smaller. It's eventually going to converge on 1 volt, right? This is 1 volt right here. And this is where things are going to eventually walk towards. But it's going to take some time to get there. This is exactly the ringing that we saw before, right? There is another example in the notes which you can look at more in detail, so you can see this play out over a longer period of time. But long story short, this is the source of where this ringing comes from. And unfortunately, the very tactics that we use to most efficiently deliver the voltage from a source to a load, from a transistor to the input of the next NAND gate, the worse we actually make this ringing problem, right? Because we're going to have a high positive reflection coefficient on the on the load side, and a very high negative reflection coefficient on the generator side. And that's how we get ringing. So with that in mind, we are going to pause right here. And the next video, we're going to talk about some techniques that we might use to mitigate or to reduce this ringing in order to prevent some of the deleterious impacts in circuits.